This is a walkthrough of Problem 3 on Exam 2 of Module 9 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 3 has a circular loop of wire fixed in a field, has a diameter of 10 centimeters and a resistance 0.02 ohms. The magnetic field is changing, pierces this loop at a right angle. From 0 to 2 seconds, the field's constant 200 millitesla out of the page. From 2 to 4, it drops from 200 millitesla out of the page to 200 millitesla into the page. From 4 to 6, it's constant, 200 millitesla into the page. And then from 6 to 7, it linearly returns to plus 200 millitesla, which is 200 millitesla out of the page. On a neat, well-labeled graph, plot the current in the loop as a function of time. Define a clockwise current as positive and a counterclockwise current as negative. A lot going on here. Let's start by making a table of the way the field is changing as a function of time. So from 0 to 2 seconds, it's constant at plus 200. From 2 to 4, it goes linearly from plus 200 to minus 200. From 4 to 6, it's constant at minus 200. From 6 to 7, it goes back to plus 200 from minus 200. This is just what's in the problem, but written this way, it's easier to keep track of. The area of the loop in the field is constant. The loop's not moving. There's only going to be an induced current when the magnetic field is changing. And the magnetic field is changing from 2 to 4 and from 6 to 7. Otherwise, there's not going to be any current in the loop. So we need the current. The current is V over R. We have the resistance R. We need the voltage, the EMF. That's the rate of change of the flux, which is the rate of change of B times A. The area is constant. We can pull that out. We multiply by the rate of change of the B field. So we need the area of the loop A. The radius is 5 centimeters. Putting it in meters, we get the area of the loop, 7.854 times 10 to the minus 3 square meters. From 2 to 4 seconds, the magnetic field changes from plus 200 to minus 200. That's a change of 400 in 2 seconds. So the rate of change of the B field is 400 millitesla divided by 2 seconds, which is 200 millitesla every second. With the area, we can get the rate of change of the flux and hence the EMF. The EMF is A times dB dt. There's the area, there's the rate of change of the flux in SI units, and we get 1.57 millivolts, 1.57 times 10 to the minus 3 volts. That's IR, and we have the resistance, so we can calculate the current. The current is 78.5 milliamps. We're going to get the direction later. Now we're going to go from 6 to 7. From 6 to 7, the B field goes from minus 200 to plus 200 in only 1 second. So that's a change of 400 millitesla each second. The area is the same as it was before. The EMF is now twice as big because the field's changing twice as fast, 3.142 millivolts. That's IR. The resistance is the same. The current's going to be twice as high. That's 1.57 milliamps, or 157 milliamps. Now we can get the directions. From 2 to 4 seconds, the field shrinks from 200 millitesla out of the page to 200 millitesla into the page. So the field's shrinking out of the page. The B field from the loop is going to want to add to that. So the B field, the current is going counterclockwise. That will produce a field that's out of the page. From 6 to 7 seconds, the field's coming up from minus 200 to plus 200. To oppose that change, the current is going to want to go clockwise, which produces a field into the page inside the loop. So now we have the magnitudes and directions. All that remains is to draw a plot. Remembering that clockwise current is positive. So when the field goes from plus 200 to minus 200, it's counterclockwise, which was why we put it negative here. Negative 78 plus 157 milliamps. Got the units in there on the horizontal axis and the units in there on the vertical axis. That plot tells the entire story of the current versus time. That's problem 3.